Thank you all for joining the third USPA technical training webinar. And today we have Dr. John Thornley and Andrew Daggett to give us a talk on the piles in permafrost from introduction to design. It's going to be 1 hour long, and I'll spend the first few minutes to introduce our speakers, and then they will use about 45 minutes and to present this topic, and then we'll use the last about 10 minutes for questions and answers. So John, if you have the next slides, and feel free to. And well, maybe come back to the agenda, but first, the serious speakers and introductions. Well, first of all, my name is Ming Xiao. I'm a professor of civil engineering at Penn State, and I'm the current president of the US Permafrost Association. And the USPA successfully held 2 webinars last year. And this year, and we have at least 5 scheduled, and likely, and we'll have more. So this is the first webinar in this year. You can see on the table, and there are more to come. So stay tuned for the announcement. So next slide. Well, the webinar series is sponsored by several generous donors. We have the AFI, and we have Shannon Wilson and P&D engineers, Geowatershed Scientific, BD Stream, and individual sponsor Catherine Schneider. If you have next slide. So our speakers, Dr. John Thornley is a professional engineer and a geotechnical engineer, and with WSP USA. He has been practicing for nearly 20 years, and he has provided design and construction oversight for pile foundation projects across Alaska and also in other states as well. Dr. Thornley is the past president of the US Permafrost Association, and is a chair of the Structures and Foundations Committee of the ASCE's Cold Region Engineering Division. Our speaker, Andrew Daggett, is a professional engineer and also geotechnical engineer, and also with WSP USA. Andrew has more than 10 years of working experience, practicing experience. He has extensive design and construction experience with the pile foundations across Alaska in frozen and unfrozen conditions. So with that, and I'll turn this to John and Andrew.
Great. Thanks for joining us today, and hope that everybody's staying warm and comfortable. If you're like us, it's a bit chilly outside, but what better thing to talk about on a cold day than piles in permafrost? So thanks everybody for being here, and hopefully there's something useful that you gained from today's discussion. And thanks, Ming, for the kind introductions. So looking forward to today's presentation. So we've already had a couple presentations through the USPA and others related to permafrost, some permafrost terms and so on. And so I just wanted to do a quick revisit of some terms related to permafrost that we'll be hitting on fairly regularly throughout today's discussion. And so this is on the right-hand side is what we call a whiplash curve or a trumpet curve, where we can describe the behavior of the permafrost environment, with at least the subsurface conditions from a temperature standpoint. And what you'll find throughout today's discussion is that temperature is a significant factor in pile design. And so understanding the key terms with respect to permafrost, and let me see if I can turn on a pointer here just to point around to things. Some key terms that we'll talk about a bit later are active layer. So this is the layer that seasonally freezes and thaws. We'll talk about permafrost. there's your standard definition of permafrost, but what we typically will have is this trumpet curve that captures all of the temperatures throughout the year of your permafrost soil down to the point of 0 annual amplitude, where everything kind of stays steady and follows the geothermal gradient. And so with that, the other piece that we also want to touch on is this term ad freeze. And the way that I like to describe it is that licking that flagpole issue, as you fix your tongue to that flagpole, that bond between the flagpole and now your tongue is an example of ad freeze. And so we'll be talking about ad freeze quite a bit with the bond between the soil and the pile, and this is a nice kind of visual of what's going on there. And I think we can all picture that, even if we haven't personally experienced doing that. So with that, I stole this from Dr. Romanovsky's presentation late last year, and I think this is let me see if I can, I don't know how to hide this. You do this here, Ming, maybe you can hide for me. Controls. There you go. All right, there we go. Okay, now we can talk business. So I think, to sum up this slide, Alaska is warming, and this is part of the genesis of the discussion that we wanted to have in today's presentation. Is this kind of underlying issue throughout Alaska that we have this warming condition, and some interesting data that's been collected, and I find this very striking, is that at 20 meters or 60 feet or so depth, you see that there's a significant warming since the 1970s until today, giving you the insight that it's not just the air temperature that we're seeing as warming, is that the general trend in permafrost, especially up on the north slope, is that there's a significant amount of warming over time. And so I think that's something that is going to kind of permeate throughout our presentation today, is this critical aspect with pile design related to temperatures and especially the change in temperature over design. And as design engineers, this is an aspect of pile design that we feel is quite important. So with that, I'll turn it over to Andrew. Maybe I will. There we go. All right.
So we're going to start talking about our warming climate temperatures. We can look back at the historical, and we have that nice trend. So we can always draw trend lines of what ground temperatures do. But I mean, as we're going to learn in future presentations, you can take this and try to predict what ground temperatures are. It's going to be outside the scope, but for this, you need to understand what the climate projections are, and that goes back to the importance of pile design. So if we're trying to design something for 50 years, what are we going to do? We cannot design something for today's temperature and expect it to work in 50 years. We're seeing that right now with things that were designed in 1980. We're currently retrofitting across the state to improve the foundation or change the performance of it and assess it again, because what they designed for in 1980 is no longer valid in 2023. So if we want to actually look at what's going to happen in the future, let's start talking about air temperatures. And right here we have a projection air temperatures for Utqiagvik. So we can go with our mean annual air temperature back in 1970 of about 8 degrees Fahrenheit. And then if we want to talk about something in 2090, we could be looking at 25 degrees under median climate. And so what we've shown here is the median is if you took all of your global climate models and ran the projections, something like 48 different projections with the change in concentration pathways, and you were to go ahead and look at the 50th percentile of your mean annual air temperatures, that's what we're calling the median. And the extreme is we look at the 90th percentile of our global climate models. So this already tells us right now that there's 10% of the global climate model projections, which suggest that the mean annual air temperature will be above 32 degrees by 2070. And this is a significant finding, because that tells us if we want something to be out there in 2070, we cannot rely on just traditional air temperatures alone, because we have a high risk that you could be looking at problems come by 2070, 2080. So it's always a very important step to try to understand this. But there is variabilities in these models, and we could see the variability can be somewhere between a 2-degree change to a 25-degree change in 2080. So that you have to kind of assess what and go into the design of what we actually want to use.
All right, so now we're going to get into kind of the meat of the matter, pile foundations, and that's going to be the predominant discussion of today's presentation. I do want to point out too that there is a reference throughout here of UFC 3-130-03, and that's actually a new UFC document that will be coming out, pile or foundation design in frozen and freezing conditions, and that is part of a series of UFCs that are being updated right now, and we helped a little bit with that process, and so we're presenting some of these figures that you'll find in that document. So there's a number of different pile foundation options. You can see here slurry pile, driven pile, drilled piles. And it's important to note that in the Arctic, piles are widely used to support structures, a variety of structures, towers, schools, bulk fuel facilities, and so on. And part of this comes through the fact that you can construct these systems throughout the year. It's very common to have wintertime construction, as well as summertime construction, depending on the location and the access to that site. Also, one of the things that these piles do is they carry the loads from those structures down below the active layer, where you have this seasonal freezing and thawing and freezing and thawing year in, year out. You're able to transfer those loads down into the ground. And the other piece is cost efficiency. So you see very little concrete in the Arctic, and where you do see it, it's oftentimes precast, and a lot of that has to do with cost of materials. And so I used as an example here from a rough order cost perspective, here in Anchorage, Alaska, where Andrew and I are sitting right now, cost of a cubic yard of concrete is roughly $150 per cubic yard, whereas out in rural Alaska, it can be on the order of $1,500 to $2,500 a cubic yard. And so it's at least an order of magnitude more expensive to construct with concrete. And so pile foundation options tend to be more common. They also allow for better Arctic design for keeping frozen ground frozen. So now we're going to get into the ad-freeze pile design. And just wanted to talk about a few important aspects of ad-freeze pile design, and that's the summer and winter design conditions for piles. And so in the summertime, you have a load on a pile, say, and that load is transferred down into the permafrost, and so you have this thawed zone, that active layer, and you have the permafrost zone. And so the permafrost, you may have an end-bearing component, and you'll have this ad-freeze component, and those actually take the loads from the surface and the thawed soil down through the pile and into the permafrost. In the fall and winter, you can actually have frozen soil near the surface. You might have a talc or a thawed zone below that active layer and the top of your permafrost. And so this part would represent a talc if that's present. And what happens there is you've got this frozen soil that is potentially even frost jacking your pile or pushing your pile upwards, which resists your load. You may also have this downward load from the thawed soil, and then you have the permafrost as well, and that could be end-bearing and skin as well. And so this, what this illustrates, or what this attempts to illustrate, is that one of the things you'll need to consider as you do a pile design is where are your loads coming from, and to understand that they change throughout the year, and that you need to accommodate that for your design. And this, one of the things that's kind of interesting is lightly loaded piles are especially susceptible to the fall and winter frost heave condition, where you end up with an embedment that is intended to resist the force from frost heave. And so accounting for that in your design is important.
With a traditional, assumed frost force of 40 psi, which is commonly used for a lot of designs across the active layer, you could see that is, in most cases, going to control your design, unless we're talking about heavy buildings. So it's very important to consider the frost jacking force on this pile.
With that, Andrew.
So when we start our ad-freeze pile design, there's a number of things that we need to understand. The things that we've kind of already talked about a little bit about before, but the other one would be start of the ground conditions. And in the previous webinar, we discussed the exploration and how we would collect this. But we have some critical things that we need to get from this. And
we'll pick it up.
all right, so it's very important to kind of consider things that we're going to get from the ground conditions, and then the design criteria like we talked about before. So this is a good start, is where do we go when we start with our pile design? And I think the first question we need to ask ourselves is, are we trying to design something for warm or cold conditions? So we kind of go down the list, what are we going to do? And we should probably mostly be talking about cold temperatures and conditions here. So then once we've decided we have cold conditions, we then start to talk about the behavior, ice rich versus ice poor. ice-rich material is going to have high ice contents. We're going to see a lot of settlement when they're thawed out, and more importantly, they will see significant creep movement during the life of the pile, which limits the capacity that we can be using. Ice pour, you can differentiate when we have our bulk unit weight higher than 106 pounds per cubic foot. So when we start talking about our cold temperatures here, the next step would be, well, how do we want to install this? What's the best way to do it? So we have a couple of different options here. We have the slurry piles. You could be traditional driving piles into the ground. And you have vibratory methods. So it really is important to pick the right method for the conditions, or you're going to end up spending all day trying to install a pile and get nowhere. Or trying to drive a pile into hard frozen ground and you're going to destroy the pile. So we then can move into some nominal ideas of the add-freeze pile capacity. There is a lot of different sources out there which have done measured load tests. So they provide useful information for trying to get some initial estimates of pile capacity. It's mostly considering ice pour materials. One thing to consider would be is where you might see a failure if we're talking about a slurry installed pile, where you're going to drill the hole, put the pile in, backfill it full of sand slurry around it. So are we going to see a failure between the soil and the slurry, or are we going to see a failure between the slurry and the pile? And when we're talking about our ice pour conditions, you tend to actually see failures between the slurry and the pile. So if you're going to take this, you can go off of actually your type of slurry you're using and not so much have to worry about the type of soil there. So there is two important concepts there. I mean, you can get a ultimate add-freeze strength, but this is something you would never design for because it has a lot of movement associated with it. So if we want something like an average sustainable strength, that's normally considered 1 inch in 100 years, 1 inch in 20 years, whatever your design criteria may be.
Provided that you accommodate for your temperatures.
Provided you accommodate for your temperatures. So it's important to kind of go off of what is our creep limited add-freeze strength here, and that's this average sustainable strength. So if we were to look at a quick example for this, we have an add-freeze pile that needs to be installed in Utqiagvik with our ground temperatures from 28 to about 22 degrees across the depth of this. We can see, like we talked about before, this is a single point winter temperature. So in design, we would truly want to actually consider our summer temperatures, where our active layer is, what this might look like in the future. But for our example, we're going to kind of just run with this number of a cold permafrost, which is going to be installed in a silt and sand material, which is going to be would be found to be ice poor with little salinity. So if we're going to come up with a strength for our pile capacity, we can break our graph into a couple of different things. So if we look at the upper 10 feet of it, or the 3 meters, we're going to get that average temperature somewhere around -2 degrees C. And then we start this at 5 feet or 1.5 meters to kind of discount the active layer that we may have it for the site. So we found that from our graph, we can get a add-freeze strength of 120 kPa. But since this was a sand slurry with a steel pile, we can adjust this by a factor of 1.5. So we're going to get 180 would be our sustainable add-freeze strength for it. And then for the rest of the pile, it's extremely cold and we're down at about -4 degrees, where we're going to have our sustainable strengths of 190, which converts to the 285. So if we take this across the length and the diameter of the pile, we're going to come up with a total capacity of about 3,500 kilonewtons. So ice creeps, and so from that, your soils are going to creep depending on the amount of ice on them. So it's important to kind of understand that. And right here, we've looked at 2 different soils. Both of them are actually ice poor soils, but you can see that we're going to get a different applied shaft stress or your add-freeze stress depending on the normalized pile displacement that we would like to use. So we need to understand the temperatures and our pile displacement to move into what our add-freeze strength is going to be. When we start talking about the creep-related movement, a very important consideration would be salinity. Do we have salts in the material? Utqiagvik is actually known for having very high salinities on the order of 50 parts per thousand or higher, which will have a significant effect. So we could see this graph here. You want to bring up your pointer?
Sure.
And if we look at our very top curve, we're going to be looking at our creep rate of 0 parts per thousand, which would kind of more relate to what we saw before. What is our strain going to be versus the stress, which then goes into our add-freeze strength. So then as you start to increase your salinity, we're going to find this one is fresh water there, 18 parts per thousand, 25 parts per thousand, and 35 parts per thousand. And so your 40 parts per thousand changes your freezing point depression by 1 degree. So that's one thing to kind of consider is you're no longer going to be freezing, of course, at 32 degrees. You'll have your change of freezing. So when we start talking about salinity, we're going to see drastic changes in our add-freeze strength. So we go over here for one soil at -5 degrees. Up there, we're going to have a add-freeze strength of 0 salinity right here. And then if we go down to 35 parts per thousand, so we've dropped from our add-freeze strength from 160 to 20 just by changing our salinity to 35 parts per thousand. So if you are in saline conditions, it is imperative that we include this reduction, or we are going to see unacceptable movement. So when you move from axial loading, the next thing we want to start talking about is lateral loading. The easiest approach would be to go with a point of fixity, which can be assumed to be about 1 foot below the active layer for a lot of typical situations.
Assuming you have no talc formed.
Assuming you have no talc formed, yes. And so, but again, with this, the soils are going to continue to creep. So if you start having a sustained load on this, you can expect to see creep movement when we're talking about lateral pile deflection. So one approach would be to go with the PY methodology, which is commonly used for assessing lateral strength in unfrozen soils. We're not going to really get into the details of that, but the PY curve is essentially you're looking at the load per inch versus inches to tell you how much what the soil performance is, and you're going to find a series of these curves at different depths to relate your pile to this. So we want to take frozen soils and then start looking at that with a PY methodology. The one approach would be Crothers came up with this approach where you can use your undrained shear strength of your soils in your frozen conditions. So right here we have a fine grain material and what your shear strength might be with your various temperatures. And then from that, we would need to reduce our strength depending on the length of the load. So if the load is going to be continuous for 20 years, the strength is going to be reduced by 0.3. Multiply that and you'll have a tiny strength left. And then you can get your reference strain, which is needed to calculate your PY curve. And with those two pieces of information, you can generate PY curves to be used in a traditional lateral analysis.
Great. So a few other considerations. So you've got the creep, axial, and lateral loading parameters that you'll evaluate. We also have a few others. We've mentioned climate change impacts. So down drag, in similar fashion to what we do in thawed soils. So with respect to the neutral plane analysis. And then also the changes in axial and lateral loading over time. As your active layer gets greater, your lateral loading on your pile will potentially get higher as well. And so those are important factors to keep in mind. We also mentioned earlier frost heave. So the upper right-hand photo is a photo of a driven H pile in Fairbanks. And you can see the paint where the paint was painted at the ground surface back in the day, but that pile has since jacked over time and essentially wasn't long enough to resist the frost jacking forces that Andrew mentioned before. And you can actually see the conduit that's being ripped out of the ground as well as that pile continues to jack into the air. Tensile loads are another one. So evaluating tensile loads, obviously you would not include your end-bearing component, but you'd be looking at the tensile skin friction and potentially a reduced factor on that as well. Cyclic loads. Cyclic loads are not as common anymore as they have been in the past due to machine damping and other things, but cyclic loads are also one that will change drastically the behavior of your pile performance over time. And then lastly, passive and active cooling. We're not going to get into cooling today. What's one thing that's very common in pile design, especially as you're trying to control your ground temperatures, is the use of thermal siphons or other cooling, and that's going to be addressed in a subsequent presentation later this spring. And so, just want to hint to that as something that's upcoming here, as something that's important. So lastly, we'd be amiss if we didn't talk about constructability considerations. One of the important pieces of any pile program is really understanding the performance of that pile. And so it's very common in especially permafrost soils to perform load testing and look at the behavior of those piles over time, and these load tests are actually pretty tricky. So they take a little bit of effort to develop a program or protocol for testing. But ASTM D5780 provides some guidance on that documentation. Construction observation, just as with every other part of the construction process, it's important to verify that you have the soil types and conditions that you thought you had when you were in the design process. And so providing that construction observation over time, as during the construction, looking at depths of the piles, did they actually get down to where we needed to go? How did the drilling go? How was the slurry quality if you did a slurry pile? And so on, to capture and make sure that the best practices were followed during construction, because the best design is only as good as the construction that actually occurs afterwards. That's one piece. And then time, right? Add freeze capacity actually requires frozen conditions, obviously, but it's something that takes a little bit of time to evaluate. And so looking at how long it will take to freeze your pile back is oftentimes part of the design process to let the contractor know when they can actually start building the structure on top of the piles, because that is an important piece of the process of gaining that capacity for those piles. All right, and so lastly, we kind of sped through a few things here so we could keep on time. We've got a list of resources. Andrew, I don't know if you want to talk about that.
So there's just a lot of different resources out there that we've kind of touched on, but probably a good starting point would be the new UFC that's coming out. And from there, you'll find references to very classic papers, such as the Weaver, Morgenstern and Weaver, for an overall pile design. And then what's, of course, from ground engineering from Andersland and Ladanye.
Great. And with that, I think we caught up Ming from our little delay due to some technical difficulties.
Great. Thank you, John. Thank you, Andrew, and for sharing your experience and expertise with us. And we have some questions, and we'll try to answer all of them in the next about 12 minutes. And I'm going to read out the questions to you and then see if you can answer. Okay, great. So I'll try to and read out the questions in the sequence that they appear. And the first one is, how do you consider the tangential heave stress for lightweight structures, such as the solar panel piles? And which code do you use?
That's a great one. I will say that I think one of the important pieces just underlying this whole process is that there's very little in the way of code to provide guidance on this. And so, there's part of it is experience, part of it is understanding the literature and understanding the research that's gone into this design. With respect to tangential forces, there is, we actually looked at this on some fiberglass piles that we were looking at for a project a number of years ago, and we evaluated what those potential tangential forces were going to be and whether they would actually crush the pile. And so we tend not to see, if you're using traditional steel, that tangential forces are significant enough to cause distress. But certainly, if you're using some alternative materials, you'd want to consider that. And there's some material in the literature regarding those forces, and nothing beats a lab test. So even if you have to do a full scale test on that, just looking at how that material behaves as those tangential forces develop during the freezing process, it would be a really good idea.
Thank you, John. Another quick question about the clarification of the drag load and the frost jacking force. Are they the same?
So the answer in the short of it is no. Frost heave forces typically act vertically upwards, and they tend to pull the pile out of the ground. Down drag is kind of an interesting one because there's a few different sources of potential down drag conditions. One is just that development of the talc below the active layer as the permafrost, surface of permafrost is receding and thawing out. And as you develop that talc, you'll have some potential reconsolidation of that frozen material becoming thawed, and that will act as a down drag load on your pile. The second is probably the one that I find more interesting as an earthquake engineer is the liquefaction induced down drag forces that may act, and that's kind of a more traditional pile impact, and you can follow fairly traditional methods to evaluate those down drag forces. Anything to add, Andrew?
No, it's just that the liquefaction concern is commonly going to be a problem with these freshly thawed soils because you have a lot of excess water. So if we're talking our ice pore sands and everything else that suddenly are now going to have excess water, we need to be looking at immediately after thawing, could you have liquefaction in that? In long term, when your pore water pressures equalize, it may not be a problem, but it goes to your design length and the importance and risk tolerance of the design.
Thank you. Oh, I saw two participants raise hands, and so maybe if you can just type your question or comments and enter Q&A, and I can share that with all of us. Question on the driven helical piles. The question was, how do drilled helical piles compare with the slurry or driven piles in permafrost, and how do they perform?
That's another great question, and it's something that's going to go back to the importance of a load test. If you think that we're not getting enough capacity out of a traditional slurry pile, you can go with a helical pile. Helical piles can be used for slurry applications, or they can be kind of advanced in.
And one of the things I think that's interesting about helicals in general, and these can be fairly small helicals. There's Arctic Foundations has a really interesting application where they've got a small band helical that actually shifts the failure from the pile surface out into the slurry, and so that's kind of an interesting piece where you gain additional capacity through the change in the failure surface, if you will, and out into more of the slurry and the surrounding soil rather than the pile interface. And so I will caution the overall helicals in thawed soils are essentially big screws that you screw into the ground. And in some cases, in frozen soils, permafrost especially, you may not be able to actually advance those more traditional helicals into the ground. And so, some planning and some serious consideration with respect to large diameter helicals or more traditional helicals are certainly worth thinking about. But then there's a few other flavors of helicals that we described just recently, such as the Arctic Foundation's solution that are interesting and do provide some additional capacity.
I mean, short answer is you do see a good increase in strength for just adding some very limited helical flights on the outside of the pile, which just stick out a couple of inches. It doesn't even need to be a full bearing plate, but by having these little miniature helices installed on the tip of your pile, you could be increasing your strengths, add-free strengths, 20% or more.
Well, you said a pile should be deeper to resist frost jacking. Is there any rule of thumb on how much deeper?
You have to kind of look at the frost jacking force. So if we stuck with our 40 psi over 4 feet, that's going to come up with a pretty big load. So we take that load and decide on how much of a factor of safety do we want. You could probably just use a factor of safety of 1 if we're neglecting any sort of building load onto it, and just make sure that your actual add-freeze capacity is going to resist the frost jacking load.
Yeah, just as kind of an example of that in Anchorage here, where we're not dealing with permafrost specifically, but we definitely are dealing with deep seasonal frost. Typical light poles that are supported by piles tend to be on the order of 20 to 25 feet in the ground to resist that seasonal frost, throughout the winter. And so it always is a bit shocking to structural engineers and others who aren't used to practicing in this kind of environment to have piles that deep, for just a measly little light pole. So
we rarely use piles any shallower than 30 feet across the state for any application.
Yeah.
Thank you. For a freeze pile, how long do you have to wait to load on such pile?
First, it depends on when the pile was installed. Like we've talked about before, wintertime construction is ideal for installing your add-freeze piles, and you can take advantage of some of those temperatures. In summer, you could be waiting a long time. And the simplest way to probably do that is to kind of monitor it. So if you're installing a slurry pile, it's very easy to take a sealed PVC conduit and drop it right next to your pile during installation and measure temperatures. Your freeze back is probably going to be on the order of about a week, 2 weeks in a lot of situations if you want to get a full freeze back down to temperatures.
And it's also a function of the slurry temperature when at time of construction, right? If you start off with a very hot slurry, you'll actually do quite a bit of damage to the permafrost surrounding before. And so all that has to heal back, and you have to have this phase change from liquid to a solid. And so it is a function of the slurry temperature as well. So
during most construction projects for things, it's not really an issue because it should freeze back by the time you get the rest of everything ready to go, weld on the pile caps and get everything set. But it is something where the contractor needs to be prepared to monitor it and have this measurement before they're actually going to start dropping their beams on.
Thank you. A question on whether the active layer is considered part of a permafrost. I can answer that no, and active layer is not a part of the permafrost. And then there's a question about the PY method. How do you treat the thawed layer above the active layer?
Your thawed layer would be treated exactly like you would for unfrozen soils.
So yeah, oftentimes you discount the upper portion because you're not going to develop those kinds of passive pressures. And so, yeah, it's a traditional PY considerations for thawed soil.
Yeah, I mean, there's your lateral resistance in frozen soils is going to be so great in the frozen material, the permafrost, that the unfrozen doesn't really matter unless you're talking like a deep talc located above it.
Thank you. Well, it's 3 o'clock Eastern time, and since John, Andrew, you are here, and I like to use a maximum of 5 minutes of your time, if that's okay, to answer some of questions.
Sure. No, happy to do it.
Thank you. I appreciate it. And for others, and if you feel free to leave, and you have to, and then this video webinar is recorded, and you can always come back to listen to the questions and answers. So yeah, just 5 more minutes, and I'll read a few more questions. Question on the group effect. That is, let me see where the question is. What's the best approach towards assessing group effect of axial or lateral capacity piles?
Don't do it. Don't put your piles close together. But for that, it becomes a very complicated question, and it's going to take a lot of literature research. So
yeah, best practice is to keep the spacing, 3 diameters or greater, because we want to try to avoid those group effects.
I can't think of any resources which they've looked at group effects in frozen soils.
Okay. Well, a question about your thoughts on friction reduction products in the active layer.
They can work, but long term, we've found it's not something that we like to rely on. I mean, it's
yeah. So maybe we can step back and just say what some of those products are, because some people on the call may not know what we're talking about here. But in some cases, to reduce the frost jacking forces and other interactions near the surface, piles will be wrapped in visqueen or sonotubes, or there's a whole host of different kinds of materials out there that people try to keep the pile and the seasonally frozen or freezing ground from interacting with each other. And so just as just a definition of what we're talking about there. And you see this in the villages around like timber piles where there's kind of this visqueen that's sticking out, or plastic wrap that's been sticking out. And so it tends to not hold up over time. And so if you seem to see that these forces are becoming challenging on your structure, sometimes you'll have to reinstall or come up with other methods. But from a short-term standpoint, they seem to work okay, but from long-term, not as much.
Sleeving is still an option.
Yeah.
If you wanted to do like a real sleeve and install a bigger steel pile, and then you're in pile through that, then yes, you can get some reduction. But if you're just a simple product like visqueen is not going to cut it for a critical structure.
Yeah, and some 20+ year design life. Yeah.
Okay, thank you. We have a lot more questions, and then I can read. So I'm going to read the last question, and this is probably not an easy one to address. How do you retrofit failed buildings foundations built on piles that were designed 50 years ago? About retrofitting of those older design building foundations.
The first thing would want to do is you really need to understand why it failed. So it's going to be your importance of the geotechnical investigation to go out there and actually get drilling right next to these piles to get temperatures. Without having temperatures, you can't do anything for a retrofit. If it looks like it's just a steady increase of temperatures due to your warming air temperature, then a thermosiphon is a great option. You can go in there, and if you have the access, you can install the thermosiphon next to it to see that reduction. Other times, it's going to be try to identify what the cause of this is. If you're seeing water migration through the active layer, then you need to start looking at site improvement.
Trying to control that water, yeah, because water, we say this a lot, and it's pretty true. Is water is probably the biggest reason that geotechnical engineers have a job, and water tends to cause us a lot of heartache and hassle. And so, oftentimes in these failed conditions, if it's not the temperature, it's likely water. So, and Andrew is spot on. You can't understand the problem until you have a sense for the ground temperatures, especially for permafrost specifically. Yeah.
But it is a very challenging concept, and a lot of times you probably can't retrofit it, and you're instead installing a new foundation. So sometimes it's hard to rely on a thermosiphon because you could have some unintended consequences. Like now you're looking at more frost jacking than you expect and you had ever designed for before. So in those cases, you have to look in marginal permafrost. Sometimes you declare it a lost cause and you have to design for an unfrozen pile.
Great. Thank you. Thank you, Dr. John Thornley and Andrew Daggett from WSP USA for volunteering your time and share with us your knowledge and expertise. So this concludes our webinar today, and I'll follow up with the email and with the PowerPoint and the recorded webinar link. So thank you all for joining the webinar, and stay tuned for the next one to come. Okay.
Yeah, thank you.
Thank you so much.